Okay, so in this video we'll be reviewing how to do a surface integral over a circle in Cartesian coordinates. And to begin, let's review why we would want to do this integral in Cartesian coordinates and not polar coordinates, because this integral is actually not very difficult in polar coordinates, but it is pretty difficult in Cartesian coordinates. And the reason is, a lot of times in engineering we have field variables that are constant along a line. So for example, hydrostatic pressure is constant at a given elevation. So hydrostatic pressure would be constant along this x, just like this. And it's easier to integrate a variable that's only varying in one direction than a variable that is varying in two directions. So oftentimes, it's easier for us to do a Cartesian integral of engineering quantities than a polar integral of engineering quantities, even if the base integral of the area is easier in polar coordinates. So it's a good exercise to know how to do this integral and integrals of other shapes in Cartesian coordinates in the event that you need to be integrating engineering field variables that are constant along Cartesian geometries like this. So to begin, what we'll do then is we'll first look at the general equation for a circle. So we have a circle centered at 0, 0 here, and we know the general equation for a circle is x minus h squared plus y minus k squared equals r squared. And the center of that circle would then be at hk, so h and k. And the equation for this circle is x squared plus y squared equals r squared. So in this video, I'm just going to present the solution to this problem, and a successful result will be if we can return the actual area of a circle, which is equal to pi r squared. So I'm going to have kind of the steps on the screen. Feel free to pause and study as you like. I'm just going to talk over some of the more nuanced points, and we'll try and get through this pretty quickly. So to begin, what we want to do is, if we're going to integrate something over a surface, we need a differential area to integrate with. So in this case, what we're going to do is we're going to use a two-dimensional differential area, as you see here. So we have this little dA, and it has a height dy and a width dx. And if we kind of zoom in on that differential element, we again have this, we have this inverted here actually. So this, that's shown, is actually dy, and this is dx. And what we'll see is, as dx and dy approach 0, dA approaches dx dy. So in other words, as dx and dy become really, really small quantities, this shape approaches the shape of a rectangle, and so its area approaches dx times dy. So now that we have this really tiny little rectangle of area dx dy, if we were to sum a bunch of these little rectangles over the entire circle, we'll get the entire area of the circle. But to do that, what we need to do is find our limits of integration. So if we sum this little differential area from this point to this point, so negative r to positive r, and we sum it from this left curve to this right curve, then what we're going to get is a bunch of rows of these differential elements from left to right that cover the entire circle. And we get this equation from the left-hand side and the right-hand side from the equation of the circle solved for x, right? So again, we're really just summing from this point to this point and from this curve to this curve. And if you do that, you'll get a bunch of rows of these tiny little differential elements, and that entire sequence of differential elements will cover the entire area of the circle. So we're going to show that on the next slide here, actually. And just as I kind of described earlier, if we're summing these little differential areas, these little differential elements, from negative r to positive r, and from this left-hand curve to this right-hand curve, again, the left-hand curve being this equation and the right-hand curve being this equation, then what we end up getting is just sequences of horizontal rows of these differential elements that cover the entire circle, going from bottom to top. And what we would then say is A, or the area of the full circle, is the integral over the entire area of the circle A of the differential area dA. And to break that into a two-dimensional integral, you would see that we're actually summing from y equals negative r to y equals positive r, as we mentioned, and we're summing from x equals negative square root of r squared minus y squared to x equals positive square root of r squared minus y squared. And we're summing that differential area dA, that little green rectangle that we showed in the previous slide. Now, that dA, as we've already went over, is actually equal to dx dy. And this is the two-dimensional integral that we actually need to solve for to sum over the entire area of the circle. Now, another way you could actually do this is if you want to use one-dimensional calculus instead of two-dimensional calculus, your differential area could actually look something more like this, where you have a finite width and you have an infinitesimal height. So this would be dy still, but this would now be w. This width would be w, and this would be your differential element, and your dA would then be dA is equal to w dy. Now w, in this case, would be equal to the value at this right-hand curve minus the value at this left-hand curve. So your W would be this quantity minus this quantity. So again, you're not getting away from using the equation of the circle solved for x in either case, but with this dA, you can get away with a single dimensional integral. With the dA that we have originally drawn, you have a two-dimensional integral. Really, the complexity is about the same, but that's an alternative differential element that you could use. So now at this point, we're really just solving this integral that we had on the previous slide. This integral we begin with. So this is the integral from x equals negative square root of r squared minus y squared to x equals positive square root of r squared minus y squared of dx. So this is actually a pretty self-explanatory integral. This is essentially that width of that finite differential element that we talked about. And so it ends up coming out to square root of r squared minus y squared minus negative square root of r squared minus y squared, or 2 times the square root of r squared minus y squared, and we still have this integral in y on the outside. Now, when we get to this step, we notice, okay, well, our integrand is only a function of y because r is constant, so we can actually solve this integral straight up. However, this integral right here is non-trivial. It's not an easy integral to perform, so what we're going to want to do is use trigonometric substitution to make this a simpler integral and solve that integral instead. So let's go to the next slide and look at how we use trigonometric substitution to simplify this result. So again, trigonometric substitution basically says, let's assume a solution for the form of y that's more convenient than the integrand we currently have. And again, we do call that trigonometric substitution when that substitution or that assumed solution is a trigonometric function. So we're going to assume then that there is a solution of the form y equals r times sine of u, and so dy du is equal to r cosine of u, and therefore dy is approximately equal to r times cosine of u du, and we use this approximate notation because treating derivatives as fractions is a little bit dubious, but we can do it in a case like this. So the next question is, why would we come up with this assumed solution? Why would we assume that this function could be a substitute for y? Because it seems like it's kind of out of nowhere. And in some cases, it is out of nowhere. In some cases, this is just the trigonometric substitution is a guess, or is from working backwards from a more difficult integral. In this case, it is not a guess. What you end up doing is if you draw this circle that we're integrating over, and we kind of draw a triangle. So if we look at some point here shown in blue, it has an x-coordinate and a y-coordinate. The y-coordinate is this leg of the right triangle. The x-coordinate is this leg of the right triangle. And the angle of that triangle right here is u. So what you end up getting, and of course the hypotenuse is the radius of the circle r. So what you end up getting is sine of u is equal to y over r, and therefore y is equal to r times sine of u. So we can assume there's a solution of the form y equals r times sine of u because geometry is telling us that there is a form of the solution y equals r times sine of u. So it's a very well-informed guess. And what's worth noting here is when we have this assumed form of the solution y equals r times sine of u, we see that when y is equal to positive r, u, or the angle, is equal to positive pi over 2. And when y equals negative r, u is equal to negative pi over 2. So when y equals positive r, we're up here, that angle is positive pi over 2. And when y equals negative r, this angle is negative pi over 2. And this is going to be useful because we're going to need to do a change of limits of integration along with our change of variables, which we'll show in the next slide. So again, we have that original difficult integral here where we're integrating from y equals negative r to y equals positive r with an integrand 2 times square root of r squared minus y squared dy. We have our substitution here, and plugging these substituted variables into the integral, what we end up getting is this a equals integral from y equals negative r to positive r of this integrand turns into the integral from u equals negative pi over 2 to u equals positive pi over 2 of the integrand 2 times the square root of r squared minus r squared times sine squared of u times r cosine of u du. So where does all this stuff come from? So to begin, we're now integrating with respect to u rather than y. So we need to change our limits of integration to u instead of y. So when y equals positive r, u is equal to positive pi over 2. When y equals negative r, u is equal to negative pi over 2. And again, here we have our 2 times the square root of r squared. We still have that. But y is r sine of u, so this is where we get this r squared sine squared of u, and dy is r cosine u du, and that's where we get this r cosine u du. So now we're going to proceed to the simplification step. Now what we end up getting is, if we look at that previous step that we had, and we factor out the r squared, we see that within the radical here, we have the quantity 1 minus sine squared of u. Well, if you recall that sine squared of u plus cosine squared of u is equal to 1, you could see that this radical, this square root here breaks down into the square root of r squared times the square root of cosine squared of u. We still have our 2 out here. We still have our r cosine u du out here. And we still have our limits of integration in terms of u, again, because we're integrating with respect to u now instead of y. So now that we're at this step of the integral, we have to ask ourselves, when we take these square roots, is it going to be the positive quantity or the negative quantity? Because when you take a square root, it could be positive or negative. In this case, it helps to remember that this part of the integrand right here represents 2 times the square root of r squared minus y squared, which represents the x integral, or the Riemann sum, the summation of all those positive differential elements in x from the left-hand curve to the right-hand curve. So this integral should be positive because it's summing a bunch of positive differential elements in x. So this quantity should be positive, and so this quantity should also be positive. So we're going to take the positive square root on both counts. So the square root of r squared is just r, and the square root of cosine squared of u is cosine of u. Simplifying this, we get 2 times the integral from u equals negative pi over 2 to u equals positive pi over 2 of r squared cosine squared u du. And now we're going to have to use a couple more trigonometric identities to simplify this, so let's proceed. So now, simplifying that previous integral that we got from the previous slide a little bit more, we see that we end up with the integral of cosine squared of u du. And unfortunately, the integral of cosine squared u du is also non-trivial. It's not an easy integral to perform. However, if you remember the double angle formula, you'll remember that cosine of 2u is equal to cosine squared of u minus sine squared of u. So what we can end up doing here is, if we combine the double angle formula with your standard trigonometric identity, cosine squared of u plus sine squared of u is equal to 1, you could find that cosine squared of u is equal to cosine of 2u over 2 plus 1/2. So again, this quantity right here just comes from combining your double angle formula, again, cosine of 2u equals cosine squared of u minus sine squared of u, with your standard trigonometric identity, which is sine squared of u plus cosine squared of u equals 1. So combining those two results you in this expression right here for cosine squared of u. And what we can just do is plug this expression in right here, and now we have the integral of cosine of 2u over 2 plus 1/2. So that's the integrand now instead of cosine squared of u. We still have our 2r squared on the outside. We're still integrating with respect to u, and we still have our limits of integration from negative pi over 2 to positive pi over 2 in u. For this first integral right here, so let's first split this integrand up into 2 parts. What we're going to do then is pull out this 1/2, and then we have this integral right here, which is just equals pi over 2 minus negative pi over 2, which is pi over 2 plus pi over 2, or in other words, pi, but we still have that 1/2 out there, so we have the pi over 2, and this integral then just descends into pi over 2. This integral right here, we end up getting, we pull out the 1/2 as shown here, but we still have this integral of cosine of 2u du, and this is not so simple of an integral. It's simpler than some of the other ones we've done, but again, it requires a special method. We're going to use u substitution here to accomplish this integral, and we'll show that on the next slide. So then let's let t equal 2u, and therefore dt equals 2 du. And making these substitutions, you could see that, we're still keeping this pi over 2 on the outside, which again is just a result of this integral of 1/2 over here kind of descended down. So with this pi over 2 on the outside, we're just going to kind of leave that alone. We make these substitutions, cosine of 2u becomes cosine of t. Then we multiply that by 2 over 2, and then we take the 2 in the numerator and multiply it by du, and that gives us dt, which is where this dt comes from. We still have a 1/2. We bring that outside the integral, so this 1/2 becomes a 1/4. Now we have 1/4 times the integral from t equals negative pi to t equals positive pi of cosine of t dt. And again, because we've changed variables, again, we need to change our limits of integration from u, which is the previous integral, to t, which is the current integral. So we're now integrating from t equals negative pi to t equals positive pi, because again, when u equals negative pi over 2, t equals negative pi. When u equals positive pi over 2, t equals positive pi. So now this integral we know is just sine of t. Plus some integration constant evaluated over these limits of integration. So we can see that the final result is we have this 2r squared still on the outside. It's been on the outside for a long time here. And now we multiply that by 1/4, which is the 1/4 outside that integral, times this definite integral, which is sine of pi minus sine of negative pi. This actually ends up equaling 0. This is 0 right here. So we end up getting 1/4 times 0 plus pi over 2. Since we still have the 2r squared outside, what we end up getting is 2r squared times pi over 2. The 2's cancel, and you get that the area, the final area, the simplified area, is indeed pi r squared. Okay, so I hope that helped. I tried to go over some of the more nuanced points that I didn't see in other derivations out there. Hopefully this helped a bit and didn't take too long in getting to the point. I really appreciate you watching. Thank you very, very much, and I will see you next time.